My name is Ning. I'm from the University of Alberta. I'm happy to be here and present our work on paraphrase identification via textual inference. This is teamwork with Dr. Bradley Hauer, J. Riley, and Professor Greg Kondrak. Our research was supported by Insert and Amy. We start with the task we mainly focused on in this work. The first one is natural language inference, NLI. It involves three labels that describe the relationship between two sentences: entailment, contradiction, and neutral. Considering the following two sentences. Sentence 1, this man is suffering. Sentence 2, a man is on water. The later sentence can be inferred from the former sentence given a broader context to make it clear that suffering here does not mean website browsing, but an aquatic activity. The second task we cared about is paraphrase identification, PI. It is the task of deciding whether two sentences are in the paraphrase relation, or we say whether they convey the same meaning. Despite their distinct objectives between NLI and PI, an underlying connection actually exists here that paraphrasing corresponds to bidirectional textual entailment, which has been notably underexplored in empirical investigations and lacks a theoretical formalization. In response, we introduce our work as the first theoretical formalization and thus a novel method as the practical reduction of PI to NLI. Here, a P to Q task reduction is to solve an instance of a problem P by combining the solutions of one or more instances of Q. In this work, we take PI as the problem P and NLI as the Q, thus to solve PI using instance of NLI. Based on that, we provide a theoretical task reduction showing how PI can be reduced to NLI. We conducted extensive evaluation across both zero-shot and fine-tuning settings on 6 PI datasets. Interestingly, we found that fine-tuned NLI models can outperform dedicated PI models on the PI dataset. Our task reduction stands on the task to identify the four sentence level relations. As shown in the figure, there are textual entailment, textual inference, semantic equivalence, and paraphrase. They are grouped vertically given whether the relation is asymmetric or symmetric, and also grouped horizontally given the need for the context. In the following slide, we will define the tasks for each relation. We start with equivalence and paraphrasing. Semantic equivalence SEQ is defined to determine if the sentences S1 and S2 convey the same meaning. Paraphrase relation PR is to determine whether the sentences S1 and S2 convey the same meaning given the context C. Thus, PR is a contextual generalization of SEQ. Putting together, we come up with a relationship in between that if the sentences S1 and S2 convey the same meaning given all the context, then they convey the same meaning and thus achieve semantic equivalence. For example, in sentence 1, we must work hard to win this election, and in sentence 2, the Democrats must work hard to win this election. Taking these two as the input, PR would return true if we consider the broader context that we in the sentence 1 refers to the Democrat in the sentence 2. However, SEQ will return false as in some context that we in the sentence 1 might actually refer to the others. Now we proceed with entailment and inference. Textual entailment, TE, is to decide whether the sentence 2 can be inferred from sentence 1. Textual inference, TI, is to determine whether sentence 2 can be inferred from sentence 1 given the context C. Similarly, TI is a contextual generalization of TE. Thus, we can put them together and come up with a relationship in between that if the sentence 2 can be inferred from the sentence 1 given all the context, then the sentence 2 can be inferred from sentence 1, thus achieve the entailment relation. Considering the same example as we mentioned at the beginning, TI would return true if considering that suffering is more likely to mean an aquatic activity. However, TE would return false due to the missing of the specification of the word suffering. Finally, we introduce our proposition here. Given context C, sentences S1 and S2 are paraphrased if and only if they can mutually infer from each other. In practice, we consider context includes common sense and word knowledge. Also, when talking about the real data, we assume context is embedded in the data distribution and also the agreement achieved by all the data annotators. To allow fine-tuning AI models on the PI dataset, we propose a data adaptation process. For positive PI instances, we convert each positive PI instance into two different AI positive instances, one in each direction. For negative PI instances, we generate a negative AI instance in one randomly selected direction. The label is also randomly selected as either contradiction or neutral, thus a random sampling from 4 possible options. Here are the results of our fine-tuned PI to AI models. As shown in the bar chart, we can see that our method can achieve competitive performance as the previous PI models. Particularly, PI to AI in fact outperforms PI models on 4 out of 6 benchmarks. We found that PulseQP and PulseWiki include several examples. As applying PI to AI needs to predict the textual inference relation in each direction. Therefore, the impact of these several examples becomes more obvious due to the error accumulation from making the predictions twice. In the application study, we also implement the PI method ourselves in a more controlled setting, where all methods are using the same language models with the classification head initialized from scratch. As shown in the bar chart, our PI to AI method continues to lead on non-pulse dataset. This consistent result confirms our proposed task reduction, and we can conclude an interesting findings that fine-tuned AI models can outperform dedicated PI models on PI dataset via our proposed PI to AI reduction. We further investigate the impact of the context by observing the change in decision boundary. We found that applying AI model to solve PI tasks in a zero-shot manner leads to different outcomes across dataset. Thus, a paraphrase identified in one dataset might not necessarily be considered a valid paraphrase in the other. We also found that after fine-tuning, the AI model will change its decision boundary to identify paraphrase for that dataset better, thus leading to a more balanced result. We regard this change as how models learn the context inherent in each PI dataset. We have presented our work, the first attempt to reduce PI to NLI. Our work showed that PI can be reduced to NLI theoretically and empirically. In experiment, we found that fine-tuned NLI models can outperform dedicated PI models on PI dataset. In addition, by applying our method in a zero-shot setting, we are able to find limitations in the current PI dataset. We also have some research questions for future. Can we use NLI to refine PI data? Can we use PI models to solve NLI? Or can we come up with a single system to solve both tasks? So please follow our GitHub repository for our data, code, and more details. That's the end of the presentation. Thank you for your attention.